In this unit, we are going to discuss sampling distributions, which is what arises when you talk about or consider taking many samples of the same size from a population, such as pollsters when they do this around an election. And using these sampling distributions, you can discuss and understand how much variability you should see in your samples. So one of the main applications of statistical methods is to use sample data to draw conclusions about populations. And as a result, we need to know how to make use of sample data to answer questions about the larger group of individuals that are represented by the ones in the sample. We will study the reasoning that allows researchers to reach conclusions about an entire population on the basis of a small sample. In general, this follows the following steps. First, pose a question about a population. So, for example, we could ask, what proportion of college students finish in 4 years? Then collect a sample from the population and measure the variable of interest. So if you're going to test that talk about that first question, you'd want to sample people, college students from lots of places. Answer the question about the sample, and then using statistical theory, determine how close the sample answer is to the true answer for the population. Before we start, we're going to review some vocabulary. So a parameter, or population parameter, remember we talked about this in an early lesson, is a number that is a summary characteristic of a population, random situation, or comparison of populations. So this is the true unchanging value that you can't find. So we assume that this parameter has a fixed or unchanging value. The value of the parameter is not known and will never be known, as you can't measure every single unit in the population. Your goal is to estimate this parameter. A statistic, or sample statistic, is a number computed from a set of sample values taken from a larger population. It is a numerical summary of the sample data, and the possible values of a sample statistic are variable, as in you will get different results with different samples, and will be different from one sample to the next. So in each situation, explain whether the value given in bold print is a statistic or a parameter. A polling organization samples 1,000 individuals nationwide and finds that 72% of those sampled favor tougher penalties for persons convicted of drunk driving. Well, we sampled 1,000 adults, not every single adult nationwide. So this is a statistic. And it's taken from a sample. In the year 2000 census, the U.S. Census Bureau found that the median age of all American citizens was about 35 years. Well, since we're talking about all Americans and allegedly all Americans were measured, this is a parameter. Taken from the entire A writer wants to know how many typing mistakes there are in his manuscript. So he hires a proofreader who reads the entire manuscript and finds 15 errors. Well, since the proofreader read the entire manuscript, which is the sort of world that we're talking about here, this is also a parameter. So taken from the population. He didn't just read a sample of pages, he read all of them. So the results in this unit are going to be used for the rest of the course to make conclusions about parameters, things we can't find, on the basis of statistics, things we estimate from samples. The procedures used for making these conclusions are called inference procedures, are called statistical inference procedures. And the two most common procedures are confidence intervals and hypothesis testing. And we've done baby examples of both of those in this course, so let's just recall what they are. So first, a confidence interval is an interval of values that the researcher is fairly certain will cover the true unknown value of the parameter. You can think about this as a range of plausible values in some sense. And in other words, what you can do is you can use a confidence interval to estimate the value of your population parameter. You know it falls between some number and some other number. So this will give a range of plausible values. Hypothesis testing or significance testing uses sample data in an attempt to reject a hypothesis about the population. There's something you want to disprove. Usually researchers want to reject the notion that chance alone can explain your sample results. So we are going to change our focus to testing hypotheses about population parameters. So for example, is the normal body temperature actually 8.6 degrees Fahrenheit or something else? The first thing we have to do in this case is assign something called a null value. And a null value is a value that implies nothing interesting is happening. For a weight loss clinic trying to figure out if their methods are effective, the null value would be 0, as in no weight loss is happening. In testing whether the average body temperature really is 98.6 degrees Fahrenheit, the null value would be 98.6. In most cases, researchers hope to show that the null value is not correct, which allows them to reject the null hypothesis. So you assume the null hypothesis is true, and you show that your sample data is so unlikely that it just couldn't have possibly been true. When we perform a hypothesis test, we first obtain a sample, compute a sample statistic. This might be a proportion or a mean, and then we assess how likely this observed value is if the null value of the parameter is true. The phrase statistically significant is used when the sample statistic would not be likely if the null value were correct. You use the phrase statistically significant when you reject your null hypothesis. Those things are equivalent. A report in Newsweek about the relationship among diet, genes, and disease discussed the E4 allele for a protein known as ApoE and said that an estimated 15 to 30% of the population has at least one copy of the allele. People who have this allele are at a higher risk for diabetes, heart disease, and Alzheimer's. So first of all, what is the population parameter of interest in the quote? Well, we care about first of all, population parameters can be means or proportions. So you should say what you're talking about here, if it's a mean or a proportion. We have 15 to 30%. That means you're talking about a proportion. So we're interested in the proportion. And then of what group? So the proportion of, we'll say just the population, which could be all people, who have at least one copy of this allele. But the kicker there, one thing I'm really looking for is, do you understand we're talking about a proportion or a percentage of people who display this trait? Would it make more sense to find a confidence interval for the population parameter that you described in Part A, or to conduct a hypothesis test for a specific null value? So let's just look at the hypothesis test for a second. If you're going to look at the hypothesis test, there has to be a value you think maybe is plausible or something like that, and then you want to reject that. And there's no obvious plausible result here. So I think in this case, a confidence interval is more appropriate. Because you may not have a guess for what the true population proportion is. And what's nice is the confidence interval will give a range of potential proportions. So, and the confidence interval gives a range of potential proportions. And actually, there's a pretty fun book called Statistics Done Wrong, and one thing that this book talks about is the importance of confidence intervals and how they really are better than hypothesis tests almost all the time, because it's far more informative to have this range of plausible values like that's given there. So you understand how, and you can understand how confident the researchers are based on how tight that interval is. Whereas a null hypothesis or hypothesis test, you just reject or accept you reject the null hypothesis or fail to reject it, and that has less information. The phrase an estimated 15 to 30% indicates the scientists don't know precisely what percentage of the population has this allele. Explain why they don't know. Well, they don't know precisely how many people have this allele because they can't possibly measure everybody. So the scientists could not possibly measure everyone. In the population to find the true proportion. And we can say that the interval gives an idea of what this may be. So one of the most important skills that a good researcher needs is the ability to translate curiosity about something into a question that can be answered using statistics. So the first thing you have to do is formulate a question about a parameter, and you have to know what kind of parameter you're talking about. Is it a mean? Is it a proportion? Is it a difference of means? So in this unit, we're going to formulate and answer questions about the 5 different situations represented by 5 different parameters. So for categorical variables, we have 2 big things. One, population proportion. In that case, the population parameter is P, and the sample statistic is P hat. So for example, the proportion of UAF students who are female. We may estimate this using a sample. And one thing to note is that proportions are going to fall between 0 and 1. A difference in 2 population proportions. The population parameter is P1 minus P2, and the sample statistic is P1 hat minus P2 hat. So, for example, suppose P1 was the proportion of females at UAF. P2 is the proportion of male students. And we were interested in P1 minus P2, as in how different are these proportions? Are they approximately equal? Is there a higher proportion of females? Something like this. But the kicker here is that we have 2 different groups. So both of these are for categorical variables. Next, for quantitative variables, we have 3 situations. One, population mean. In this case, the population parameter is represented by mu, that's the true value of the mean, and the sample statistic is x bar. So, for example, what is the average height of a UAF student? We could maybe use this class to find a sample, find an average height of people in this class, find x bar to estimate the true average height of all students at UAF. Now, a population mean of paired differences. Now, in this case, you have measurements that are paired and the differences are computed. For example, before, after, in a weight loss study or matched pair design. So in this case, the population parameter is mu with a subscript of d, and the sample statistic is called d bar. So for example, you do the before and after measurements on a weight loss plan or a drug trial, something like this. But the point is you have an obvious pairing of values. Difference in 2 population means. In this case, the population parameter is mu1 minus mu2, where mu1 and mu2 are the means of each of your populations. And the sample statistic is x1 bar minus x2 bar. And in this case, the thing to note is that these 2 samples are not coupled in any way. And they must be independent. And for example, one thing you could be comparing as the average height of women at UAF versus average height of men. So there should be no obvious pairing. And what we'll focus on for the rest of this lesson is just distinguishing between paired data and also if do you have a parameter or do you have a sample statistic. So explain whether p hat or p is the correct statistical notation for each proportion described. The proportion that smokes in a randomly selected sample of n equals 300 students in the 11th and 12th grade. Well, first of all, this is a proportion, so it's going to be a p something, and since it was a sample of 300, it's p hat. So since from a sample. The proportion that smokes among all students in the 11th and 12th grades in the US, and this is p, as it is all students. A student doing a project for a statistics class wants to estimate the difference between the mean number of music CDs owned by male and female students. He surveys 50 male students and 45 female students about the number of music CDs they own, and the mean number for the males is 110, and the mean number for the females is 90. Obviously, this question's a little bit dated, as most people don't own CDs these days. What is the research question of interest for the survey? Well, I think it is the difference between the mean number of CDs owned between these two groups. So the question is, what is the difference between the mean number of CDs owned by women and by men? What is the population parameter in this study? Well, we're talking about a difference in two populations. That's the first thing to notice. And the parameter means the true value. And we're also talking about means, which means we're talking about a mu and not a p. So if we let mu sub 1 equal the population mean number of CDs owned by men, and mu2 equal the true population mean number of CDs owned by women, we are interested in the parameter mu1 minus mu2. What is this difference? What is the value of the sample estimate or statistic in this study? And what is the appropriate notation? Well, once we shift to sample data, instead of mu, we use x bar. So we have x1 bar minus x2 bar. And your book adopts the convention that usually the larger number is first, just to keep answers positive. And that's why in the previous part of this problem I defined mu1 to be the population mean number of CDs owned by males. So the sample data said that the mean number of CDs for males was 110 and for females was 90. And that comes out to be a difference of 20. So x1 bar minus x2 bar is 20. Another important thing to be able to do is to distinguish between paired data and two independent samples. So for each of the following research questions, would it make more sense to collect independent samples or paired data? In the US, what is the average age difference between husbands and wives? Well, as a husband and wife makes a pretty obvious pair, this should be paired data. And if you have paired data, tell me what makes the pairs. A husband and wife make a pair. What is the difference in average ages at which teachers and plumbers retire? Well, there's no obvious connection between teachers and plumbers, so this would be independent samples. And the reason there being that teachers and plumbers are two separate independent groups. What is the difference in average salaries for high school graduates and college graduates? Once again, there probably isn't any obvious pairing here, so this would be independent samples. So high school graduates. Two separate independent groups. And finally, we're going to give an overview of sampling distributions before in the next lesson we kind of delve into them with more detail. So here's the basic idea. Think of taking a random sample or conducting an experiment as one big random circumstance. For example, suppose you survey 1,000 adults to determine who they will vote for in an election. You find that 40% are going to vote for candidate A, and the 60% are for candidate B. You can then repeat this survey with another new sample of 1,000 people. And in that new sample, your proportions voting for candidates A and B will probably be different than the first sample. You could then repeat this process again and again and again, obtaining many samples of 1,000 individuals. So the sampling distribution for a statistic is the probability distribution of possible values of the statistic for repeated samples, and here's the kicker, of the same size taken from the sample population. So you think about doing this experiment over and over and over, and a question you're asking is how are these proportions going to change from one experiment to the next? How much variability will there be? And one can guess that if you have large samples, those proportions would not vary as much as if you had small samples. So consider a situation in which a sample of 100 SAT scores is taken from the population of all people who took the test in a given year. Which would be more spread out? The sampling distribution of the sample means for 100 SAT scores, or a histogram of the 100 SAT scores reported in one sample? Okay, so what we have, the sampling distribution talks about if you repeatedly took samples of 100 and found their averages, how would the averages vary from sample to sample? So this is a variation in averages versus just the sample of 100 itself. Now, the people who are sort of special and on the far ends of the spectrum are going to get evened out in the averages, whereas they don't in the specific sample. So that means that we're looking for which one is spread out, the latter would be more spread out. So here's that written down. The histogram of the 100 SAT scores in one sample would be more spread out. The extreme values get averaged in with the other values in the sampling distribution. Okay, here is a common format for the 5 sampling distributions. So in each case, as long as certain conditions are met, the sampling distribution is approximately normal. The mean of the sampling distribution is the population parameter that corresponds to the sample statistic. So the mean of the sampling distribution is the parameter that you want to know, which is estimated by your statistic. And the standard deviation of a sampling distribution measures how the values of the sample statistic may vary across different samples from the same population. So this question, and the kicker there is that they are the same size. So if you take many samples of the same size, how does the sample statistic, which could be x bar or p hat, how does that vary? So when discussing sample statistics, we want to know how much we can expect the statistic to vary over different samples of the same size. This can be accomplished by finding the standard deviation of the sample of samples. So the standard deviation of a sample mean is called the standard deviation of x bar. The standard deviation of a population parameter is called the standard deviation of p hat. To make it clear, we're talking about a standard deviation of a statistic. We use the term standard error when estimating this standard deviation. So consider a situation in which researchers measure a random sample of 50 newborn babies and the average weight is calculated. If a new random sample of 50 newborns is taken from the same population, explain whether the following would change. So the population mean mu. Okay, this is going to have no change as it is a parameter and fixed. The sample mean x bar, if you take a new sample, this will change. Now, these next two will be more obvious in the next lesson, but the standard deviation of x bar, this is actually not going to change. This is the true value. And we're going to learn a formula for that in a later lesson that tells us that the standard deviation of x bar is sigma over root n, where sigma is the true population standard deviation. But for now, this is telling us how are our samples going to vary. So what is the true value of the variability of these samples of a given size? The standard error of x bar, this is an estimate of the standard deviation of x bar, and we'll learn in a later lesson that the formula for this, oops, I should say SE, not SD, is S over root n, where S is the sample standard deviation, and as a result, this will change from sample to sample. And the sampling distribution of x bar, including its shape, mean, and standard deviation, this remains the same for all samples of the same size.